All right. Well, good morning, everyone, or good afternoon, depending on where you are. My name is Madonna Benjamin, and I am here representing the team for a CIN network. It's under a USDA grant, and we host a webinar series. We took a break since May, and it's August already. For those of you who are teaching or those of you who are looking forward to the fall. This session I also want to include Dr. Jenna Sigbert, who's is also a co-investigator, Dr. Juan Steibel and Guillaume Rosa, who are on the call currently. And we have other members, Eric Soda, Joao Dora, and Thomas Norton, and I may have missed someone.
And so, Tammy Brown-Brandel.
Tammy Brown-Brandel. Oh, and Daniel Morris. There we go. Thank you. So I would like to introduce to you Dr. Shiraz Nithirajan, who's a PhD and he's associate professor at Dalhousie University, Canada. Dr. Shiraz is now a Canadian professor. He was based in Europe, and his work is in invention, consultation, and researching in the field of digital livestock farming. Uniquely, he recently graduated with a certificate in applied data science from MIT. And he had obtained his master's and PhD in biosystems engineering from the University of Manitoba. He conducted 2 postdoctoral fellowships, one at Oak Ridge National Lab in the US, and the second at the National Food Research Institute of Japan. He's also worked at Wageningen University in the Netherlands and is collaborated with University of Guelph. Shiraz brings a multitude of academic and industrial experiences for solving practical problems in the agri-food sector. His expertise includes, not limited to, improving animal health with artificial intelligence-powered farming, unlocking unparalleled performance with big data and artificial intelligence-driven insights, and harnessing the power of AI. He's also using big data analytics and AI-powered decision and support systems. What I've noticed in many of his publications, and you'll see on the invitation that in 2023, there's a number of publications, but he's also taken the combined not only big data and analytics with livestock welfare. And I think that there's a great opportunity for Shiraz to work with different teams within our sector, as well as the stakeholders in industry. So with that, Shiraz, if you would like to take over and give your presentation. Thank you.
Yeah, thank you so much, Dr. Benjamin, and also the research consortium, which is overseeing and managing the PLF via computer vision at Michigan State University. It's really great to be here. Today, we just take maybe 30-35 minutes to briefly talk about some of the examples of computer vision instrumentation approaches in understanding the adaptation physiology, behavioral, welfare, and health-related aspects of farm animals, mainly 3 species, chickens, poultry, swine, and dairy cows. Just a glimpse of a very high-level overview of the possibilities of computer visions and some examples of what has been done in this area. So digital phenotyping is gaining really momentum, both in the United States and also in the Europe. When we use this word nowadays, we humans, we are using smartwatches, and many parameters, behavioral indicators, health-related parameters are constantly measured, like moment by moment data that is captured that provides a variety of telltale signs. So for the livestock farming, what we are looking at is how do we use this similar concept, similar phenomena to acquire new subtle signs, subtle information about farm animals. It's more of a, I would say, a cutting edge approach to understand the farm animals' emotions as well. So we can delve into clinical constructs such as aggression and lameness, which can provide very detailed insights about indicators of animal welfare, both positive, neutral, and negative indicators, and also the productivity indices of the farm animals. So it's very interdependent. There are many components associated under the phenotyping. When we look at the high-level behavioral indicators, digital phenotyping helps to identify and interpret such as hedonic activity or gait pattern, how the animal is moving around, how long they are sitting and standing. We are not talking about the gross level. We are looking at the moment by moment data, the minuscule level changes, how these subtle data can provide new information than the data that's available at the gross level, very high level. So these indicators can provide changes in the intensity of the emotions change, but also can be used to detect and manage bigger issues like aggression, tail biting, feather pecking, etc. When we look at the low-level futures, at the core of digital phenotyping, we can understand the location type. It could be an extensive farming system, such as animals grazing outdoor, or it could be an indoor activities such as poultry and swine-related farming, and also using vocalization and acoustic environmental data. When we capture these variety of data using a multitude of sensors, we can understand the location, movement, vocalization, and translate these raw data into animal emotion states. In terms of behavior and cognition, the broader context is absolutely essential in the analysis. So when we connect, when we create that linkage between the indicator and the construct, we can have a better understanding of the animal well-being, social dynamics. How do they talk to each other? How do a certain group of animals in a large flock of birds in the poultry industry dictate, decide, and influence the behavior of a whole lot of population? Those kind of questions, hypotheses and perspectives, we can investigate using digital phenotyping with the aid of instrumentation and sensor technologies. Obviously, ethical considerations and future plays a significant role. We have to recognize in terms of using the technologies and ensuring accuracy and also responsible application. So with the advent of explainable AI, it becomes very important for us to explain how do we use this technology, what is the implications behind it. Sometimes there is unconscious bias and there is an unknown involved. What we don't know, we don't know. Can we be able to unravel that don't know component in terms of applying artificial intelligence and sensor technologies in acquiring data, in developing trends, patterns, and insights? That becomes really, really important. So we see some examples here. So when I use the word emotions, the word can be divided into two components. Emotion. E stands for energy here, energy in motion. The energy comes in variety of forms. For example, the blood composition, the blood always circulates in the body. So it carries cortisol, neuroendocrines, and lactate, and other components such as ketosis and beta-hydroxybutyrate and other metabolic components. Some of these biochemical markers are always present, but only when it exceeds a certain threshold level, it becomes problematic. The animal could become probably experiencing metabolic disorders or ketosis, or stress level drastically changes, and so on. So this is an energy in motion that can possibly be acquired non-invasively using some of the biosensors and biochemical, minimally invasive sensor-based instrumentation. Second energy is what we call as bioelectrical energy. It's related to the heart rate, the respiration rate, how the lung capacity changes over a period of time. So we get collect time frequency data here. And of course, the brain-related activity. For example, we could use fNIRS or other EEG-related wearable devices to acquire the data to understand the affective states or the mental capacity of the farm animals. Of course, heat has been studied quite a bit. Thermal energy is quite common. We acquire changes in the signatures on the face of the animals, and then we say something about how the bird experiences stress. The either poultry birds, or swine, or dairy cow, they always do thermoregulation by breathing, inhalation and exhalation, and trying to cool down the internal temperature of the body. So there is always a bit of an activity in terms of heat changes that happens surrounding the nasal region, in addition to the ear as well as along the ear region. So once we know the subtle changes in these regions along with the other body, for example, the rectal region, the movement of the tail, we could create a correlation with the changes in the other component of the energy in the body of the animal to say some scientifically validated statements, develop indicators that could may perhaps serve as a telltale sign of an indicator of welfare and physical, physiological, behavioral changes within the body of the animals. Of course, sound has been looked at recently, and also the past for a swine. We have a company called Sound Talk in Belgium from Berkman's group. There is also chickens. People are looking at how do we acquire data to understand the Geckel call. How do these chickens communicate? What is it that we need to understand? Because the frequency is so less among the high noise criteria, how do we make sense out of it using data analytics? So when we combine all of these energy signatures, we could understand not only the behavioral, physiological, health-related aspects, but also, more importantly, the mental makeup or the affective states of these birds. So when I use the word emotion, again here, it is a non-tangible concept, especially for farm animals. We are still unraveling, we are still trying to understand what constitutes an emotion for a farm animal. As a animal behavior scientist, as a ethologist, as a biological engineer, we still rely upon human psychology. So there is a possibility of objectification. There is a possibility of seeing through the lens of humans in terms of understanding these emotional makeup of these farm animals. Paul Ekman is a scientist who actually came up with a variety of methodologies to determine and come up with different classes of emotions for humans. So we use that as a base and then keep on developing new indicators, new framework, new merits to establish and to create consensus. So using that consensus, we look at the different affective states. For example, it is time dependent. So we cannot label a human being as an angry person or a happy person because it fluctuates over a period of time. So is the case with the farm animals also, because the energy fluctuates and is context dependent and time dependent. So there is a true need for interdisciplinary collaborative research expectation here to be able to truly make a scientifically validated statement about the farm animal emotions here. So one of the key concept here is what I call as a balance or the intensity. So because it's time dependent, how does the intensity of the emotions changes over a period of time? That becomes crucial. For example, we developed a nice emotion measurement system using camera and other high technology tools. In a barn, it's very common. We can see mosquitoes and flies. They move around because of the cow dung and other related environmental factors, humidity. So when the fly or the mosquito sit on the ear of the dairy cow would basically flap their ears. So there is a possibility for the system to pick up as a false positive or a true negative signal. So how do we overcome that? So these type of context-dependent understanding has to be infused into the automated sensing system, welfare continuous monitoring system, to be able to really have a validated system in determining the emotions and the affective states of these farm animals. So it's much more than that. At least on the gross level, there are things that we have to go deeper and look into it for true scientific validation of a system development for emotions measurement in the sensors. The second thing is stimulus processing. For example, we induce a stimuli when we conduct an experiment to either a positive or a negative or a neutral indicator of the emotions. But there is always a gray level. Sometimes when the stimulus is being induced, based on the context, it may lie in both regions. So we have to be very careful in choosing the assumptions and the boundary conditions for the development of the systems here. A quick example in terms of chicken welfare, chicken stress measurements here. We developed what we tool using a deep learning system to understand the chicken movement, chicken activity via computer vision systems. The idea here is we install multiple cameras inside a barn, and from the top view and also from the side view, we are basically looking at how do they move around, how many steps they make towards the feeding station, how many birds try to flock together, what is their social network, what is the distance they travel or the migration coefficient each of these birds make over a period of time. So we started with a small pilot scale with 40 birds in an enclosed system. And then we are currently looking at developing to the second phase in terms of expanding to more birds in a wider angle here. Just a demo here. So what we are seeing here is a clip of the video that shows the birds moving. The system or the software we have developed is capable of differentiating. For normal human eyes, everything looks white. But based on the algorithm, the tiny little changes in the pixel density, the shape and the size of the birds, they can actually pinpoint this is chicken 1, chicken 2, chicken 3, chicken 4. So we can differentiate, we can identify and discriminate the different birds, but also how do they go from point A to point B? That can also be measured, how many meters they travel over a period of time. That information can also be pooled in via the algorithm in determining the migration coefficient of these birds. So counting, identifying the birds in terms of the differences between them and the amount of the activity or the movement they make. So when I go back here, we can see here in this, so for example, if you assume this is the barn, we have north, south, east, and west. There is a bigger gradient on the northern side compared to the second here. So we can say, based on the mathematical calculation from the results of the algorithm, the number of birds are primarily geared towards the north end of the barn compared to the eastern zone in the second figure at time point 2. So when there is a change in the wind or the humidity or the temperature conditions, how many birds make a preferred migration towards certain zone inside the poultry barn. So those kind of quantitative indices can be made. But also we can say something about the social network. How do they talk among themselves? How do they aggregate among themselves based on certain external influences in their own population or the flock? Those kind of quantitative phenotypic information can also be acquired using this information. There is a possibility to use deep learning along with the computer vision to understand the pecking behavior of these birds. So here we can see the birds, they are jumping. Again, it's an outdoor example. They are jumping and trying to peck against each other. So depending on the movement, how much vertical movement that happens, what is the amount of activity per bird, using that we can establish a framework in determining and saying something about this bird is a bit more aggressive compared to the other bird and so on. So there is a framework we could establish in determining quantitative indices using this information. So here is an example here. What we are looking at is this is another study. We induced stress in the chicken birds. We did a 40 bird study. There were two stress were induced. One is using an umbrella. We suddenly opened an umbrella and shocked the birds. In another group of birds, we used a iPhone and Android phone to play a barking sound from dog. So to create a negative induced stress. And we were interested in finding out how the vocalization changes, how the temperature on the surface of the birds, especially the eye region, the beak and region changes. Are there any correlation in terms of the heat stress and also the vocalization? Can we be able to elucidate some of the welfare indicators based on these information? So blinking also plays a role. For example, the number of blinks, this is a collaboration with the Texas A&M University to look at, they did a study on avian species for wild birds. So we were curious, is there a possibility for, the eye blink, the number of blinks they make, the heat that is exchanged coming out of the eye region, can that be an indice for welfare and correlate to the affective states of mental capacity? For example, when the in the bigger poultry industry, when the eggs hatch, these chicks, they never see their mother. So there is no possibility of social imprinting here. They have to learn everything from trial and error. As soon as they come out of the eggs, they start pecking. And then, okay, this is good, this is not good. And this big lack of social imprinting and lack of motherly affection and the influences the later life. So sometimes this can also possibly contribute to aggressiveness in the birds because of the support system in the early life. The early life conditions dictates the late life resilience and the adaptation capacity of these birds. So from this context, we were looking at how the number of blinks and the data related to visual behavior of these birds, do they have a role in the welfare? Can this possibly be a facial indicator to say something about the welfare of these birds? So we can see some of the preliminary results. We collected data via a regular camera as well as thermal camera to acquire temperature on the surface of these bodies. So we did a comprehensive study for about 12 weeks, 40 birds, the age of the birds versus the group, flock density, and the type of stress, whether it's an umbrella-based stress versus stress induced by noise, and how they create a changes in the stress on these birds, and also fluctuation in the temperature on various regions of these birds. So some of the findings, we would say that this is a quantitative examination in terms of blinking as well as facial temperature variations in relation to the stress. Definitely, there was a huge change in the beak temperature. And the animals becomes automatically quiet in terms of vocalization. As soon as the stress is indicated, they become more quieter. The vocalization, the Geckel calls changes drastically compared to the controlled birds. So they have three eyelids. Unlike human beings, upper eyelid and lower eyelid, they have a vertical eyelid nictitating membrane. That also played a significant role. So we started collecting feathers and blood samples to understand how the cortisol changes based on specific context, to understand, is there any correlation with what the instrument and cameras measure with actual changes in relation to the blink stress. So the preliminary results shows that yes, blink, the full blinks and the number of blinks can possibly be able to say something about the stress. But the biggest challenge is this is only 40 birds. When we have to scale up for 10,000 birds in a poultry barn, how much resolution we need to have in terms of acquiring the videos and images, what's the data processing capacity, how the subtle level, very, very fine scale changes that can be acquired for analysis. So those are some of the question marks still remains that need to be further investigated. Here are some examples of the thermal cameras. We acquired a variety of data in terms of understanding the series of behaviors of the poultry birds. But again, upscaling is still a challenge. So when we use a thermal camera, the distance between the camera lens to the object dictates the quality and the resolution of the data. Once the bird moves away, the resolution changes, which causes an issue in terms of the accuracy and sensitivity of the actual data we get. It's a wonderful academic study, but for practical realization for industrial applications, still more research need to be done. We went ahead and acquired a variety of vocal sounds. So the idea here is to, once we collect this data, it's pretty noisy. There is a lot of humming sound and the mechanical structure and operating happens. But we were able to use deep learning and MEL frequency MFCC coefficient in terms of subtracting the variety of noises and looking at the different smaller calls that were made by these birds. So it was quite interesting to see the variations before stress and after stress, and also how the age of the birds over a period of 12 weeks, how the bird starts to adapt, because during the first 2 weeks, they tend to feel immediately experience stress. But after 6 weeks or 7 weeks of study, they get used to that stress. They kind of expect, okay, there is really no harm. So we were able to see those changes from the data analytics in terms of the changes in the frequency and the actual smaller changes in the neural network that clearly shows that birds were able to adapt after 6 or 7 weeks if we constantly induce stress to these birds. So the methodology here is we collect data, sound data, we convert the sound data into an image, a spectrogram, what you can see here in the yellow. And then we were looking for a neural network to be able to find out what are the buried information in there. We also used MFCC. We can see some of the spectrogram signature, and went ahead and developed a variety of modeling approaches in understanding how these birds changes in their volume, the frequency, in determining the various characteristics to acquire buried information in classifying before stress and after stress, and what are the specific features that contribute to specific changes in their stress levels. Moving to the swine very quickly, we did a little study in which we employed a 3-in-1 sensor, or Internet of Things. This is a Sapphire sensor which has the capability of collecting 3 types of data: respiration data, heart rate data, and also activity or accelerometer data. We actually collected data from 40 pigs, and we ended up using up only from 5 pigs, because pigs are notoriously mischievous, playful, and started eating the sensors, then it reduced to 11 pig data, and then we were confident that only data from 5 pigs. So we did a variety of almost very extensive exploratory data using deep learning and machine learning approaches and understanding or the correlation between heart rate pattern when pigs are in isolation during feeding, when after feeding, when they are packed together, how the heart rate changes. What is the influence of respiration rate in terms of the social context? A number of questions we were asking. How does the age affect the heart rate? The gait analysis, how the gait changes in terms of the stress. Based on the accelerometer, we were able to collect 3 types of data: sagittal, lateral, and vertical, X, Y, and Z axis, and did a very exhaustive data analytics using deep learning to address a bunch of questions using deep learning. So the results are quite really interesting. We can clearly see that, when the pig age moved from 83 to 108, there is a significant change, influence in terms of the age. The pigs become slower in activity as the age increases. There is a distinct difference between pigs. We are able to also elucidate, say, a little bit something about personality. There is a bit of personality differences. Some pigs are playful, some pigs tend to be more aggressive based on the correlation and the cluster analysis and the combination of respiratory accelerometer as well as the activity data. So it's every day, 3 or 4 days a week, we were able to collect this data over a period of 12 weeks. And then we did a bunch of analysis. The data size is also a bit large, about 55 gigabyte of data acquired. Some of the preliminary analysis that shows how they are socially connected but physically isolated because they are put in crates. They can see each other, they can hear each other, but they cannot physically physically be in close. Once the feeding is finished, we open the crate and allow the pig to interact. So we can see the jump in the heart rate. Sometimes the pigs tend to mount, they demonstrate playful behavior. We were able to characterize each of these in a detailed manner based on the data we acquired. Obviously, feeding and post-feeding, they tend to lie down a lot. So we were able to correlate that information with the heat map, because simultaneously we were collecting a regular camera video and also a thermal camera along with this 3-in-1 multimodal data. We were trying to correlate with the rectal temperature, blood level, cortisol to understand the information and the linkage between the actual physiology, the behavior, and the changes in the indices as provided by these sensors and machine vision data. Some of the, here we can see the correlation map and the different parameters we measured: heart rate, breathing rate or respiration rate, variability, activity, posture, and so on. How these information and the interdependent parameters plays a significant role in providing telltale signs about the stress levels, thereby an indirect indication of affective states or mental states of these birds. Briefly, we also did a little bit of study to understand the lighting conditions, how different colors of LED influences the different behaviors. Are there any peculiar behaviors that changes between the lighting conditions? What are the advices we can provide? There are many companies nowadays, Hot Agree, there are quite a few companies, they sell different LED lighting systems. The one conclusion or finding we propose is that, hey, do not give a universal lighting. Do not put a common lighting for the full floor. Try to give a zone-wise or a localized lighting to allow the bird to choose which lighting they want to be experiencing. So this choice of this provision of choice to the birds not only improve the welfare, but also provides productivity improvement for the farmers. So that's one of the findings from this study. Obviously, red tend to provide aggression. Sometimes if they see red under the red light, birds sometimes mistakes that as a blood and start pecking more. So the aggression also tend to increase under the red LED light in comparison to white and blue light. There is no one solution. It's context-based. Age also dictates. Breeding type of the bird also dictates in terms of the choice of LED lighting to be decided. Here we can see about 23 different characteristics we acquired under various lighting conditions, and we come up with what we call as a figures of merit. We give for this specific, for example, after feeding, to induce perching and to induce resting for the birds, you provide this combination and this intensity of lighting. So that's the kind of advice we propose at the end of this study based on the data we have collected so far. There is a possibility also to predict the behavior, especially the pecking and the aggression-related behavior based on some mathematical modeling. It's still in the proof of concept. We haven't really elucidated yet, but our data indicates that, hey, use this data to develop a predictive model and come back and validate based on the observation from ethologists and behaviors. Is there a possibility, at least 80-90% of success rate in terms of predicting the aggression and behavior related indices? Couple of examples on measuring emotions in farm animals. We labeled named this software as WUR. WUR stands for Wageningen University and Research. Wolf is a playful name because Wolf is the mascot of the Wageningen University. So we collected a bunch of videos and data at different conditions. And based on some of the previous work by other groups, Emma Baxter, the Scotland rural folks, and also other folks in Switzerland, we acquire some of those basic framework to understand whether we would be able to automate the measurement of emotions just based on the facial indicators of dairy cows and pigs. There are two different approaches. One we call as an arbitrary units. What we do is the squinting of the eyes, how much pursing of the lips happens, what is the direction of the ears, whether it's symmetrical, asymmetrical, whether they're erect or droopy. We also acquire localized histogram of gradients, and using these information and correlate the actual indices: aggression, fear, pain, happiness, neutral, playfulness, and so on and so forth. Similarly, we did for pigs also. Now with the deep learning approaches, we move away from the arbitrary units because we are now not relying only on the images. We are acquiring real-time video imaging, and we use the video to be able to analyze and picking those information to understand the changes in the emotions. We also looked at the facial emotion recognition developed in Taiwan and Hong Kong and other research groups and tried to apply. Obviously, we cannot directly use that for farm animals. So we have to adapt and understand the various changes. So we were able to look at this information in terms of deep learning based neural network, ANN and CNN based metrics acquisition, but also from the arbitrary unit based traditional, the old style in terms of acquiring the information, in terms of changes in the indices as related to the different emotion makeup of these animals. A lot of applications we could see. For example, we could actually label this as Nina versus Sally versus David. We can actually individually identify the animals if we can clearly recognize these different futures, the changes in the futures of these faces of the animals. in addition to understand the mental makeup or the emotional states of these animals. There are many other applications, social network analysis, phenomics. We would be able to understand the trait between animals and between groups, using the traits to correlate the behavioral traits, physiological traits, to correlate with the genomic traits in terms of developing a phenotyping for new applications. That's also a possibility using this biometric-based behavioral pattern understanding from the vision data composed of both images and video. So just a small framework here. We think we were able to show about 13 different emotions: relaxed, alert and neutral, aggression, positive, negative, excited, relaxed, and so on. So we can see some of these, how the eyes are open, symmetric, asymmetric, forward, backward, eyes are upward, and so on. So again, we used a bunch of, the data is not big, only 153 videos and 7,800 images for the phase 1 study, just to establish, to see how much of accuracy it can give. Some of the data we collected just using a regular phone, like a handheld iPhone and Android. Some we were able to collect using advanced high-resolution camera. So it's a mixed hybrid data quality we were able to use in this particular study. Just an example of how this works based on the YOLO V4 and YOLO V5 algorithms. Again, here the take home is the balance, because it's very much time dependent, context dependent. So the intensity of the emotions changes only at a certain particular time. So it becomes very important to measure, because ethologists and behaviors would disagree if I label the bird as the animal as an angry animal or a happy animal. So, and we also need to know, when we install cameras in the farms, when we do a real-time continuous automated acquisition of data that sends information to policymakers, veterinarians, and others, we need to be ensured that the data we get is of a higher quality and of scientifically validated. So we consider a variety of approaches in terms of validating some of these tools. So it's an ongoing study, or more like a baby step. We have demonstrated, hey, it's possible. We still need to more explore. There is a lot of debate happening between the neurologists and people from animal behavioral scientists in creating a consensus about the various nitty-gritty details and nuances that falls under the bigger umbrella of emotions. So that we need to establish standards and matrices to be able to come up with a better comprehensive understanding of emotions. One of the take-home message I would like to say is that we have used thermal camera, kinetic depth, regular camera, heart rate, respiration rate, and activity. And of course, we collect blood-based data such as cortisol, neuroendocrine, rectal temperature, saliva. We take saliva and do some ELISA-based tests to understand some of the biochemical markers to correlate. That's just only one angle. We need to expand this. We need to go for 4D or 5D cameras, and also collect data using fNIRS and other instruments to acquire the brain-related information. For example, in one of the studies I showed before, the thermal video of pigs, the inner ear temperature is connected to very close physically to the brain of the pig. So there is a drastic change. When we look at the analysis of the variations in the thermal signatures, we were curious why only in the back end of the ear temperature changes drastically compared to the nasal and the eye region. So this tells that the ability of the transfer of heat varies between different regions of the faces compared to snout, eyes, ear region, tip of the ear, and so on and so forth. So a little more research needed to further validate in terms of using more multimodality data along with facial data, vocalization, activity data, olfactory breath analysis. Sometimes it can also provide information about the gut microbiome biota, gut can be directly correlated to the mental capacity, functioning capacity of these animals. So there is a little more comprehensive multimodality approaches obviously needed. A lot more need to be done for automated real-time measurements, because some of these are bits and pieces and chunks of work done here and there. But when we integrate, synthesize, create synergy, it becomes more challenging. For example, the 40 birds we studied as an academic study, obviously it does not work in industry scale. Much more need to be changed. A lot of boundary conditions and variations has to be obviously changed for a large scale adoption and application. So we have to consider cybersecurity, data security, ethical implications, farmers' perspective, because it has to be farmer-centric in terms of adoption and embracement of technologies. It's not a technology push. It has to be a pull. It has to be complementary, not replacing the employment of farmers. So these are bigger policy-related aspects we have to consider when we develop these technologies, validate these technologies for applications. Again, an emphasis on acquiring brain-based data along with the smell-related data that has still to be integrated with the existing data. I think maybe I would like to stop here. Just a picture to showcase some of the photographs I have taken during the summer term in Wageningen in the Netherlands. There is also an art show happening just 10 minutes walking distance from Arnhem, where my house was in the Netherlands. It's an open scale. About 600 people came together, students mostly. They draw a variety of arts. It's really impressive and fascinating. Thank you so much for this opportunity to connect with you, to share some of the work we have done. Maybe we can discuss, and if there are any questions, I'm happy to answer. Thank you.
Thank you so much for your presentation. Are there questions? I see there's one comment in the chat from Yenny. Thank you for the talk. In the case of the analysis on respiration rate in pigs, box plot slides, are the results adjusted for weight and sex of the animal? Thank you.
Yes, for the weight for the animal, but not yet for the sex for the animal. It's an ongoing work. Little more analysis is still yet to happen. Yeah. Because we did measure the weight of the pigs every day in the evening. We have that data. But sexes, they are mostly the same sex. So we have not really looked at, again, the data pool size. We started at 40 animals, shrink to 11 animals. And a mix of between 11 and 5 pigs. That's the data. So it's really a small amount of data we have been looking at.
So a bit of housekeeping. If you have a question, please put it in the chat, or you can raise your hand. We can see the attendees in the gallery if you raise your hand as well and you want to ask a question. This is another question from Anhan. Do chicken feathers affect the efficacy of thermal cameras and the quality of the data obtained? Thank you.
Yeah, certainly, of course. I think there is a study done in the University of Georgia, folks, Choi and his group. Yeah, so they installed on the ceiling, but we did both. We installed some on the ceiling. We had a bunch of summer students and undergraduate. They were running behind at a certain distance and acquired handling on the shoulders, because the FLI or T1020 is a little bit bulky. They were acquiring data. The feathers does affect, but we were mostly interested on the facial region, beak, the comb region, the eye region of these birds. We started studying from day 1 to week 12 over a period of a 12-week study. Feathers does affect, so that has to be considered. Some correction factor has to be applied. We developed what we call as an SSPD technique in terms of how do we overcome by shuffling data. when we collect a large amount of data, we typically, during the testing training stage, we distribute into 80-10-10 or 60-20-20. So the shuffling technique can sometimes help. Sometimes augmentation technique can overcome. But from a physiological perspective, feather does play a significant role in providing the, of course, the distance between the camera lens and the object, in this case, the chicken, also plays a significant role in the acquisition of thermal signatures.
Maybe Shelby, you see hands. I don't, so we'll take the next question in the chat. This is from Florinita. Congrats on the presentation. It's very complete work. I would like to know, after the results you have found so far, is there anything you would have done different or something you think could be missing?
We always like to do more, because sometimes it's always feels like, hey, I could have done a little more than what data analysis we have done. For example, we have this multimodal data. We were able to collect sound, thermal signatures, and video. I still have a hunch that we have not fully made use of the data. There is a lot of buried. Again, it's the resource is the biggest issue. We need a lot of people, a lot of collaboration, so we could really create new value from already sitting existing data. So it's like only surface scratch. Maybe that's the right word. We have scratched the surface. There is much yet need to be explored. Thank you. That's really a nice question.
Yeah. From Sadhu, appreciation for a detailed presentation and insights. Did your team connect with MFCC metrics, disease diagnostics, by some chance?
Mel frequency coefficient metrics to disease diagnostics? No, we have not looked at that angle yet. That could be a possible tangent we could do, yeah.
I'm glad you brought that up, because I thought it was a cage fighting an acronym. What are the critical challenges setting up in the AI-enabled IoT infrastructure for livestock data?
Challenges in setting up the AI-enabled information or Internet of Things infrastructure for livestock data. It's basically resources, money, people, time. If we have both of that in abundance, I think we could do wonders. Because we have certain frameworks established, we continuously learn from the advancements in the biomedical and defense-related technology. Sometimes we try to adopt. For me personally, my perspective and opinion is it's always the resources. If we have lots of resources, we can actually make many things happen.
I was impressed with your work on the thermal imaging. Particularly, I noticed the thermal images when the birds were pecking. I'm wondering if we would be able to determine nutritive suckling versus non-nutritive suckling in piglets based on thermal imaging, the actual motion, and if it would increase the temperature in the snout. Do you know of work? Oh, Zhao has his hand up. Okay. Go ahead, Zhao.
I mean, he can answer your question first. I mean, I can't wait.
Okay, all right.
I would say so. We have to really start investigating. Depending on the resolution of the camera, we can certainly see some changes in the temperatures. One of the bottleneck right now is automating. When we collect a lot of images, especially thermal videos, again, it's a FPS, frames per second. Each frame has certain distribution of signatures. Once we go to the second frame, the certain coordinate, here we have, let's say X100, Y100. When we go to the second frame, if the pig moves a little bit, then the actual physiology changes, which means we are not actually looking at the specific point. It moved to a different point. So we need to ensure that we are able to still point to the same physical location on the specific future. So we have to overcome that aspect. They tend to move a lot. So the movement-related artifact causes certain noise distribution in the actual quality of the data. We need to consider that. But irrespective of that, depending on the resolution of the camera, we still can do. There are also nowadays pills available, capsules, like the Ireland-based company, Anipil. There are companies in Europe also, they are selling some. So we can make them swallow. We can continuously measure pH and temperature inside the gut of the pig. And then correlate that information with the distribution of the facial changes in temperature, along with other indicators, and we can come up with a nice model.
Hey, Suresh, congratulations. Very nice presentation. I have a question related to the emotion analysis that you have. So the emotion, it's something sometimes subjective, hard to annotate, right? So my question is, what is the gold standard? How you get things like happiness, frustration, relaxing? How you generate the gold standard to train the models? How evaluate the animals to come up with the classification?
Correct. Yeah, that's a nice question. That's the biggest bottleneck, a challenge. We are trying to create consensus with the people from diverse disciplinary background. So we collect, as of now, what we do is we collect rectal temperature, we collect blood-based indicators, cortisol and lactate. We cut the hair and do analysis. We collect saliva at that particular time point and correlate that information. We also have a bunch of ethologists sitting and watching the videos, behavioral scientists watching the videos, and annotate based on the context. That annotated data is also correlated with this information. So these are the only two ways to validate as of now. But we have to still evolve. We have to come up with new approaches to further create that standard. There is a scientist in UK, Mike Mendel. His group is really far ahead. They have done wonderful work. So I think it's a common challenge among all the researchers in this area.
Okay, yeah, because it seems some of the parameters are related to the physiology, right? So, if you have high cortisol or something like this, you may say this is a stress. So some of the emotions, they are really physiological response, and some others are combination of the behavior plus physiology. But it's that's something I think when you say frustration or happiness or things like this, it's how subjective the measurement is, or how representative of a physiological state the measurement is. I mean, how you separate them.
Yeah. So it's context dependent and physiology dependent for sure. That's why we do a variety of, for example, in pigs, we try to induce states. We expose them to certain playful material and suddenly withdrew. So once we withdrew that, they experience certain frustration or the expectations changes. So there is a sudden changes in terms of the tightening of the eyes, pursing of the snout, and so on. So we do some of these behavioral experiments, providing positive, negative, and neutral related conditions, and acquire that data continuously and observe the physiology, behavioral information, and use that information in our model for further validating these systems.
That's good. Thank you very much, Suresh. Thank you.
Thank you.
Suresh, I in some of your recent publications, you talked about the use of educational tools to train. Well, you talked about avatars, or you wrote about avatars, and I wondered if you had comment on training the people aspect, the stock person, on using the information you have. I really like the idea of the art in the park display that you put up, and opening up people's perception, and that's any thoughts on using your tool for training persons?
Yeah, I wrote a book called Metaverse for Modern Animal Farming. It's in Amazon. You can go to amazon.com and search my name. It will list the book. So in the book, I think 2 chapters is about training, how we can use virtual reality, augmented reality, deepfake technology for a variety of applications. One is creating training program. Already, I know Dairy Council of America they have some programs using some of these technologies for as a training tool for dairy-related applications. But for example, in the farm also, in terms of improving the animal welfare, for example, if the mother cow is sent to slaughterhouse and the calf is missing the mother, we can actually emulate the physical appearance, the vocalization in the farm itself to create a little bit of comfort to these calf using these metaverse or the deepfake related technologies. There is a possibility to improve welfare. Again, it's a very, very gross example I'm giving you, but there are many applications we can develop using some of these technologies in improving the welfare. It has challenges also. For example, we have seen in newspapers in Russia and other countries, they put these masks, the physical reality gadgets on the eyes of the cows and try to emulate nature, like as though they are grazing outdoor, but actually they are indoor. But there is a threshold. It would work for a certain extent, and beyond that, they get used to it. They may react entirely negative. Or sometimes from an ethics perspective, we could say that we are actually violating their own rights. Animal has their own rights. We are indeed violating that. So it's very gray area. So we have to be very careful when we develop these technologies, not because some of these technologies, it's always from the production perspective, we have to consider, can we be able to ask the animals, what do they actually need? By understanding their way of communicating, so by understanding their language, and we could infuse the technologies in such a way that it's truly beneficial for their cognitive and mental capacity rather than violating their rights. So we have to be extremely understanding in terms of developing and applying these technologies.
Jenna Sigford also had a question for your eye blink work in chickens. Did you consider which eye was blinking? Brain lateralization may impact which eye.
Oh, that's a wonderful question, Dr.
Janice, did you want to add to that?
Difficult because we were working with the Texas folks, and they tend to move their head all the time, and we were able to acquire only one. No, we haven't. It's hard to answer the question. Yeah, lateralization is indeed. Yeah, that's really a very in-depth question. Thank you.
I think we'd also have to think about, of course, the video image is often reversed, right to left. So we'd have to make sure we were always tracking which it was in reality versus the video image. But yeah, something to think about if you expect to see differences under different emotional conditions, which side is blinking.
Yeah, we color the pigs, so we know that this is a pink color and blue color on one side, and then we try to always code for the pigs. For the birds, it's a bit difficult for sure.
Yeah. Interesting work, though. Regardless, it's got to start somewhere, right? So it's good to get something going on it.
Thank you. Low-hanging fruits for immediate operations in commercial chicken operations by some chance? For sure. For example, the chick track, the tool we have developed, we can definitely apply. There are quite a few companies. We have been in conversation with them. I know Thomas Norton's group from Belgium and Sweden, Oluxi and others. They were also kind of looking at along these lines. So yes, machine vision has been used. Vocalization, people have been looking at pig. It's a bit established. Soundwell is a well-established company. Georgia folks, not from UGA, but from the Atlanta, they have done a little bit of a few years ago in terms of chick talk or chick vocalization, but it need to be a bit more, we can unravel, we need to develop more, refine those development for adapting to practical applications. So the commercial applications via computer vision in terms of developing phenotyping, digital phenotyping is possible. I call this as digital markers. For example, depending on the changes in the physiological behavioral indicators, every animal have a certain digital marker. We can actually, using that like a QR code, we can actually have a digital marker for each of those animals based on interdependent complex features, digital features that extracted. So we apply those digital marker to each of those animals. Again, from a welfare perspective, we can use that. So there is a certain framework, certain protocols that can further be refined and used right away within maybe a couple of years using some of the methodologies we have developed.
Any further questions or comments from our participants? Well, Shiraz, I want to thank you to actually say the same thing that many others have said. You've done a fabulous job in giving us an overview. And as others have pointed out, it's highly appreciated. We thank you so much. And I think your goal of wanting to have more collaboration will stem from this webinar series. At least that's our hope. And this is very good work. Anyone else have a comment? We want to thank Shelby Warner, who has been working with us to keep us organized. Currently, we have around 200 people who are registered for the CIN webinar series, and this recording will be available and will be posted once Shelby's able to transcribe it. And then also we'll provide for you some stats on how many people are attending, who's attending, and a little bit more on the background of the CIN webinar series and in the next sessions. Our next session will be in September, and I'm sorry, but I didn't have that ready on who's, I think it's Optifarm is presenting. Well, we'll send that information out to you. Here we go. The next one is September speaker. It will be David Speller, founder and CEO of Optifarm. So look forward to seeing or reading from all of you. And thank you again, Shiraz, for coming. It's been a fabulous meeting.
Thank you so much. You all have a nice day. Bye.